Welcome you all. So this video related to steam turbines. So in this lecture I will explain about steam turbine efficiencies and condition for maximum efficiency of a single stage impulse turbine. So first of all we will discuss about what is efficiencies of steam turbine. So in that one, first one, define and explain blade coefficient, second nozzle efficiency, third one diagram efficiency and stage efficiency. So these terms are very important related to steam turbines or steam turbine efficiencies. The some performance parameters of steam turbines are as follows. The first one, blade coefficient. So blade coefficient is also called as nozzle velocity coefficient. The losses in the flow over blades are due to friction, leakage and turbulence. Blade coefficient is the ratio of the velocity at the exit to the velocity at the inlet of the blades. So that is, the blade coefficient is given by C of B is equals to the ratio of VR2 VR1, so that is equals to V2 by V1. The second definition for nozzle efficiency is, it is defined as the ratio of actual enthalpy change per kg of steam to the isentropic enthalpy change per kg of steam. So that is, the nozzle efficiency is equals to delta H, that is actual enthalpy change, to the delta H dash, that is isentropic enthalpy change. For impulse turbine, the nozzle efficiency is given by, so actual enthalpy drop is equals to half V1 square, and for that reason this expression becomes nozzle efficiency is equals to half V1 square to the ratio of delta H dash or isentropic enthalpy change. For in case of reaction turbine, this efficiency is given by the half V1 square minus half VR1 square minus VR2 square by the to delta H dash. So here, because in impulse turbine the pressure drop occurs only in nozzles, but in case of reaction turbine the pressure drop occurs both in moving blades as well as fixed blades. So now third one is diagram efficiency. It is also known as blade efficiency or rotor efficiency. So it is defined as the ratio of work done per kg of steam by the rotor to the energy available at the inlet per kg of steam. That is, diagram efficiency is given by, or blade efficiency is given by, the ratio of W to the E of A. So here W represents work done by the rotor or work available at the rotor, to the E of A is equals to energy available at inlet. So that is equals to work done is given by U into delta VU. Delta VU. So here delta VU is equals to VU1 plus or minus VU2. Then E of A is equals to energy available at inlet. For impulse turbine, the E of A is equals to half V1 square, that is kinetic energy is available at the inlet. And for reaction turbine, E of A is equals to half V1 square minus half VR1 square minus VR2 square. Next definition, stage efficiency. It is defined as the ratio of work done per kg of steam by the rotor to the isentropic enthalpy change per kg of steam in the nozzle. That is, the stage efficiency is equals to W, the ratio of W to delta H dash. So for impulse turbine, the stage efficiency is a product of blade efficiency and nozzle efficiency. Stage efficiency is equals to product of blade efficiency and nozzle efficiency. For the reaction turbine, once again this is expression for the stage efficiency in reaction turbines. So that is also termed as the stage efficiency is equals to product of blade efficiency and nozzle efficiency. So these are the some efficiency terms used in steam turbines. So now move on to the next very important derivations for single stage axial flow impulse turbine or the level turbine. Now show that for a single stage axial flow impulse turbine, the rotor efficiency is given by theta B is equals to 2 into phi cos alpha 1 minus phi square into 1 plus CB cos beta 2 by cos beta 1, where CB is equals to VR2 by VR1 and phi is equals to speed ratio. Beta 1 and beta 2 are rotating blade angles at inlet and exit. VR1 and VR2 are relative velocities at inlet and exit. The combined velocity diagram for an axial flow impulse turbine is as shown in figure. So this is a combined velocity diagram for single stage axial flow impulse turbine. So here delta VU is equals to the summation of VU1 plus VU2 or X1 plus X2. X1 plus X2. So now what about the distance of X1? So here X1 is equals to if you consider the cos beta 1, so at that time, so it is equals to the x1 by cos beta 1 is equals to x1 by VR1. So for that reason, the x1 is equals to VR1 cos beta 1. In similar manner, the x2 is equals to is measured in terms of cos beta 2. The cos beta 2 is equals to x2 by VR2. For that reason, x2 is equals to VR2 cos beta 2. So in similar manner, for the expression for the VU1, the tangential velocity at inlet, there is a VU1 can be termed as the cos alpha 1. The cos alpha 1 is equals to VU1 by V1. For that reason, VU1 is equals to V1 cos alpha 1. In similar manner, VU2 is taken as cos alpha 2 is equals to VU2 by V2. For that reason, the VU2 is equals to V2 cos alpha 2. So these some relations are used in order to derive the expression for this blade efficiency. So energy transfer for an axial flow turbine. Energy transfer for an axial flow turbine. The E is given as E is equals to W. So that is equals to U into delta VU. So here the U into delta VU is equals to VU1 plus VU2. So from the velocity diagram, VU1 plus VU2 is equals to x1 plus x2. VU1 plus VU2 is equals to x1 plus x2. So what about this? Say the VU1 plus VU2 is written as x1 is equals to VR1 cos beta 1. Then x2 is equals to VR2 cos beta 2. So for that reason VU1 plus VU2 is equals to VR1 cos beta 1 plus VR2 cos beta 2. So now here VR1 cos beta 1 take it outside. So at that time, say here 1 plus VR2 cos beta 2 by VR1. So now here VR1 cos beta 1 is equals to x1 and remaining these terms remain as it is, that is here 1 plus say VR2 by VR2 by VR1. So that is called as blade coefficient. This is given as a CB, that is CB taken as CB here, then cos beta 2 by cos beta 1. So where CB is equals to VR2, the ratio of VR to VR1, that is called as blade velocity coefficient. So now VU1 plus VU2 is equals to the x1 can be written as VU1 minus U. So here this x1 is once again written as VU1 minus U, then into 1 plus CB cos beta 2 by cos beta 1, that is equals to, see here VU1, the VU1 is equals to V1 cos alpha 1. VU1 is equals to V1 cos alpha 1, and this U is taken over here, that is U. So then this is taken whole as 1 plus CB cos beta 2 by cos beta 1. Then W is equals to, so then W is equals to, say this is expression W is equals to U into VU1 plus VU2. So according to this U into, so VU1 plus VU2 is here. This VU1 plus VU2 is equals to V1 cos alpha 1 minus U into 1 plus CB cos beta 2 by cos beta 1. Blade or rotor efficiency is given by, that is the ratio of work done or work available at the rotor to the energy available at the inlet. So now work available at the rotor is given by U into V1 cos alpha 1 minus U into 1 plus CB cos beta 2 by cos beta 1, and energy available at the inlet is given by kinetic energy is available at the inlet, that is half V1 square. So then let's simplify this one. After simplification we are getting the blade efficiency is, or rotor efficiency is equals to 2 into U by V1 cos alpha 1 minus U square by V1 square 1 plus CB cos beta 2 by cos beta 1. So here U by V1 is called as speed ratio, correct? That is called as what? Phi. The substitute the phi here instead of U by V1. In similar manner here U square by V1 square, that is called as what? No, speed ratio, that is a phi square. So after substituting the speed value terms in place of U by V1, the blade efficiency is equals to 2 into phi cos alpha 1 minus phi square into 1 plus CB cos beta 2 by cos beta 1. So now it is proved that the blade efficiency is equals to 2 into phi cos alpha 1 minus phi square into 1 plus CB cos beta 2 by cos beta 1. So where phi is equals to U by V1, that is the blade speed ratio. The continuation of that derivation in order to find out the maximum blade efficiency in a single stage impulse turbine. The blade efficiency for single stage impulse turbine is given by, so already this expression we derived in that previous slide, that is blade efficiency is equals to 2 into 5 cos alpha 1 minus phi square into 1 plus CB cos beta 2 by cos beta 1. The variation of blade efficiency versus speed ratio is shown in figure 6.7. Say here, in x-axis that shows what the speed ratio phi and y-axis shows the blade efficiency. See, for the maximum blade efficiency, the speed ratio is called as the optimum speed ratio. So here it shows what is optimum speed ratio. So when we are getting what the maximum blade efficiency, this point that represents what the maximum blade efficiency, and corresponding speed ratio is called as optimum speed ratio. The slope for maximum blade efficiency is the differentiating of blade efficiency with respect to speed ratio, so that is equals to 0. So now differentiating of blade efficiency expression is 2 into 5 cos alpha 1 minus phi square into 1 plus CB cos beta 2 by cos beta 1, and that expression, the blade efficiency expression, get differentiated with the speed ratio. After differentiating, we are getting the value of 2 into cos alpha 1 minus 2 phi into 1 plus CB cos beta 2 by cos beta 1 is equals to 0. That means the optimum speed ratio is equals to cos alpha 1 by 2. The optimum speed ratio is the speed ratio at which blade efficiency is the maximum. So now here the blade efficiency, the speed ratio, the optimum speed ratio is equals to, here we are getting the maximum blade efficiency. So that means now we are getting one more expression for speed ratio, that is optimum speed ratio is equals to cos alpha 1 by 2. Next, continuation of that derivation further. In order to prove what the maximum blade efficiency is equals to cos square alpha 1 by 2 into 1 plus CB cos beta 2 by cos beta 1. Once again for that single stage impulse turbine. And according to this, so here the blade efficiency for single stage impulse turbine is given by, so this is expression for blade efficiency already we derived, very first term we derived here, it is blade efficiency. Later we discussed for calculated the speed ratio phi is equals to cos alpha 1 by 2. So now the blade efficiency is the maximum, therefore the maximum blade efficiency is equals to 2 into, so instead of, in place of phi, so there are phi, in place of phi you have to substitute the value of what cos alpha 1 by 2, and here it is what phi square, that is equals to cos square alpha 1 by 2 square, that is 4. Substitute that values here, that is 2 into, so now this phi is equals to cos alpha 1 by 2, then cos alpha is there, minus once again phi square is there, that is cos alpha 1 by 2 whole square into 1 plus CB cos beta 2 by cos beta 1. So that is, there is expression for maximum blade efficiency. After simplifying that, we will get the maximum blade efficiency expression becomes the cos square alpha 1 by 2 into 1 plus CB cos beta 2 by cos beta 1. Next, prove that maximum blade efficiency for a single stage impulse turbine with equiangular rotor blades is given by maximum blade efficiency is equals to cos square alpha 1 by 2 into 1 plus CB. So where alpha 1 is the nozzle angle and CB is blade velocity coefficient. Or sometimes you will get the questions like that. Prove that maximum blade efficiency for a single stage impulse turbine with equiangular rotor blades is given by maximum blade efficiency is equals to cos square alpha 1, where alpha 1 is the nozzle angle. The maximum blade efficiency for a single stage impulse turbine is the maximum blade efficiency. Already we derived this expression, that is cos square alpha 1 by 2 into 1 plus Cb cos beta 2 by cos beta 1. So for equiangular rotor blades, so that is beta 1 is equals to beta 2. So now maximum blade efficiency is equals to cos square alpha 1 by 2 into 1 plus, so here cos beta 2 is equals to cos beta 1, because of beta 1 is equals to beta 2. So that means that is a Cb. Now it is only Cb. If no losses due to friction, leakage and turbulence in the flow over blades, that is Vr1 is equals to Vr2. So that is Cb is equals to 1. So now this equation becomes maximum blade efficiency is equals to cos square alpha 1 by 2. So here, so now Cb is equals to 1, that is 1 plus 1. So here this 2 and this 2 get cancelled. So finally maximum blade efficiency is equals to cos square alpha 1. That is the one more expression you obtain in case the blades are equiangular as well as there is no losses to the turbine. That is maximum blade efficiency is equals to cos square alpha 1. Above equation conclude that if the flow over blades does not have any losses due to friction, leakage and turbulence, then for a single stage impulse turbine with equiangular rotor blades, maximum velocity, maximum blade efficiency is same as maximum utilization factor. And this is the expression, so this is a description about the maximum efficiency in a steam turbine for different conditions. Thank you.